Good morning. Let us get started. We will first recapitulate what we were doing last time. We are saying that rate monotonic scheduling is a very popular scheduling algorithm used in almost all non-trivial applications. And we had discussed some very basic issues in rate monotonic scheduling. So, we will just review that very briefly for a couple of minutes and then we will proceed from there on. So, just recollect that we were saying that the algorithm for this is very simple. Said that the designer has to assign priority to tasks, that is proportional to the frequency of the tasks. The task having the highest frequency will have the highest priority, right. So, or in other words, the task having the lowest period will have the highest priority and the task having the highest period will have the lowest priority. And then we were discussing about the property of rate monotonic algorithm. We said that it is a static optimal static priority algorithm. Here the priorities are assigned before the system starts by the programmer during design time, and throughout the system run the priority does not does not change, and it is the optimal algorithm in the sense that if something cannot be scheduled using RMA, then we cannot have any other static priority scheduling algorithm which can schedule that same set of tasks. So, in that way this algorithm is very important. And we are trying to determine how do we know the schedulability of a set of tasks that are given to us. So, the first test that we need to do is the utilization bound. Basically, the processor cannot be used more than 100%, very simple condition here, that the utilization due to each task, that is the time of the execution time it needs divided by the period of the task, summation of that should be less than 1 or some of the utilization should be less than 1. This is the basic condition to be satisfied by any scheduler on uniprocessor. But for EDF this is both the necessary and sufficient condition, but here for RMA this is a necessary condition. If it is less than 1, then there is a chance that it will be schedulable, but it is not the sufficient condition, we will have to test further. And we had discussed about the Liu and Layland criterion proposed by Liu and Layland in 1971 through a lengthy derivation, complicated derivation, said that if the utilization due to all the tasks in the set is less than n into 2 to the power 1 by n minus 1, where n is the number of tasks that we are trying to schedule. If this is satisfied, then the set of tasks will surely be schedulable. Now, if we try to plot the total utilization due to the tasks that is achievable, or the maximum utilization for a set of tasks that is schedulable under RMA according to the Liu Layland criterion, we can substitute values for n is equal to 1, 2, 3 etc., and try to determine this utilization bound. So, if you do that, we will see that for number of tasks 1 utilization is 100% and then gradually drops as the number of tasks increases and then saturates around 0.69. So, when n becomes very large, it becomes a indeterminate form, infinity into 2 to the power 1 by infinity minus 1, and by using L'Hospital's rule we can find the bound to be 0.69. So, that means if we have large number of tasks, the maximum utilization of the CPU is about 0.7. We can't make the CPU any more busier than this. So, 30% of the CPU time will be wasted, is not it? But that is the price for meeting the deadlines for the tasks according to the Liu-Layland criterion. And then we had looked at some problems, like given a set of tasks, how do we determine whether they are schedulable? So, we just need to find the utilization due to the set of tasks. So, we find that it is 11 by 15, some of you had done last time, and then check n into 2 to the power 1 by n minus 1, which is 0.778, and since 11 by 15 is less than 0.778, the task set will be schedulable. Simple test, just put in the formula, you get whether it is schedulable or not. But the thing is that if a set of tasks fails the Liu-Layland criterion, is there a chance that they will be schedulable? Yes, it is so, because the Liu and Layland criterion is a pessimistic criterion. If it passes Liu-Layland test, then definitely it will be schedulable, but even if it fails, there is chance that still it will be RMA schedulable. And this was given by the completion time theorem by Liu and Lehoczky. So, today we will discuss about the Liu-Lehoczky criterion and we will proceed from there. So, the first utilization bound is the total processor utilization due to the set of tasks should be less than 1, and then the Liu-Layland criterion, but it is pessimistic. If it fails, we need to check further. So, that is given by the completion time theorem, it is called as the completion time theorem proposed by Liu and Lehoczky. So, this diagram says that U1 utilization bound 1, if it is less than U1, then there is a chance that the set of tasks will be schedulable. If it is more than U1, then obviously the set of tasks will not be schedulable. And if it is less than U2, that is the utilization bound 2 obtained by this n into 2 to the power n minus 1, then definitely the task set will be schedulable. As long as it is less than U2, we can positively say that E2 will run satisfactorily. But what if it exceeds U2 and less than U1? So, there is a chance that it will be schedulable, and that is given by the Liu and Lehoczky's completion time theorem. We will look at it. This theorem is very simple actually. Unlike the Liu and Layland, which we said very complex proof, here it is straightforward. So, as long as it is less than U2, less than the Liu-Layland criterion, we can without hesitation say that it will be schedulable. More than U1,
is this check 3 perfect bound or
the Lehoczky's? Yeah, we will discuss about that. The question is that whether the completion time theorem tells us precisely whether it will be schedulable or not. To a large extent, yes, but again we will see that even if it does not really satisfy Liu-Lehoczky criterion, that is the third test, still there is a small chance. We will check that. So, let us first discuss about the Liu-Lehoczky's criterion. So, this was proposed in 1989 by Liu and Lehoczky, and the theorem is very simple. The theorem says that look at the deadlines of every task and assume that the tasks are 0 phasing. So, even if some phasing information is given for the tasks, assume that all tasks have 0 phasing and then check the first deadline of every task. If every task meets its first deadline under 0 phasing, then the task set will be schedulable. So, consider 0 phasing and check whether each task will meet its first deadline. Do not have to look any further, as long as it meets the first deadline, the task set will be schedulable. But what is the reasoning behind this theorem? we will just look at the reasoning behind this theorem short while from now, but let us see using this theorem how do we check the schedulability of a task set. So, first is all the phase information we need to make 0, and then for each one we will have to draw the schedule till the first deadline and then check if the task set is schedulable, and if all the tasks is schedulable, I mean meet their first deadline, the task set will be schedulable. But the problem with this approach is that if you have let us say 10 tasks and each one has very different periods, drawing the first schedule for all of them is difficult. You should have some simpler test, we will look at that, but for 2-3 tasks definitely you can drop the schedule and conclude. So, the basic premise or the main idea behind this theorem is that for any set of tasks, the worst case schedulability or the most likeliness of them missing the schedule occurs when the task set is in phase with each other. So, if a lower priority task is out of phase with a higher priority task, then it is likely to get more CPU time, but if it is in phase with a higher priority task, then chances are that it will not meet its deadline. So, if we can check for the worst case situation, that is all tasks are in phase, then we can say that they will meet under all phasings. Now, let us just to explain this idea that when the tasks are in phase, the worst case occurs. Let us just take one example. We will take 2 tasks. T1 has execution of time 10 and period of 30, deadline of 30, and let us say phase of 0. Okay. And another task T2, execution time of 60 and period of 120 millisecond and phase of 0. Now, which will have the higher priority between T1 and T2? Yes, T1 will have higher priority because it has lower period or higher frequency. So, let us try to draw the time by which T2 will complete, that is called as the response time of T2. So, T1 is in phase with T2 because phi is equal to 0. Okay, we will also look at the same set of tasks when the phase differs, and for both of these cases we will try to find out what is the completion time of T2, and if the deadline is aggressively set, then this is the situation we will see that the deadline is likely to be missed. So, the first one, let us draw the schedule. See here T1 is the higher priority, runs for 10, and then T2 continues to run until T1 arises again, and T1 arises at what time? That is 30, right. At 30 T1 arises and T2 will be preempted, is not it, and T1 continues until 10 millisecond, that is 40, and again as soon as the CPU becomes available, T2 runs, and if we draw the schedule like this, we will see that T2 will complete at 90 millisecond, right. It will have the 60 millisecond of execution at this point 90. So, that is the response time for T2. But let us assume that T2 is out of phase with T1, that is T1 is arising after 20 millisecond, the first instance of T1 arises at after 20 millisecond. So, first T2 will run, and as soon as T1 arises it will run, and so on, and we will see that the response time is 80. So, just because they are out of phase, T2 could complete earlier. We can also try to check whether what if T1 has 0 phasing and T2 has phasing of 20 or 30. In each case, we will see that when they are in phase, the response time is the longest. So, if we can show that in the worst case, that is when the phase is 0, every task meets its first deadline, then the task set will be schedulable. As we are saying that when the number of tasks is more, it becomes difficult to draw the schedule, it takes long time and erroneous. We can have a simple formula here by which we can check each task whether it meets its first deadline. So, the formula is very intuitive. See, if we want to check whether a task Ti will meet its first deadline. Now, let us assume that T1, T2, T3, Tn are arranged in order of their period, that is T1 is highest priority and Tn is lowest priority, right. So, as long as there is a higher priority task, the rate monotonic algorithm will not allow a lower priority task to run. So, using that simple thing, that as long as there is a higher priority task, the lower priority task will not be allowed to run. So, the response time for the task Ti will be Ei plus sigma Pi by Pj ceiling into Ej. That is to be summed for all j equal to 1 to I minus 1. So, we are checking for a task Pi here. Now, we have to check whenever a higher priority task is there, it should run for Ej. Every higher priority task Tj will run for Ej, and that time Ei cannot do anything, it has to wait, right. So, during the 0 to Pi, how many instances of Pj will occur? So, let us say Pi is 100, okay. Now, P3 let us say Pi is P4, okay. P4 is 100 and P3 is let us say 30. So, how many instances of 30 will occur before 100? What do you think? 4, because at 0, 30, 60 and 90. So, 4 instances will occur. So, that is why we have made it taken a ceiling here, 100 divided by 30 ceiling. So, that will give us 4, and each time it runs it will take Ej amount of time, and if as long as for every higher priority task the CPU is yielded and Ei is taken into account, if that is less than Pi, then the task Ti will complete before Pi. Does that appear okay? Everybody is okay with this? Okay. So, this is the basic formula we will use. We will use this formula for every task to find out whether it will meet its first deadline. Let us take an example. So, 3 tasks here, 20 millisecond and 100 millisecond, that is T1, T2 runtime is 30 millisecond and period is 150, T3 is 60 and 200. Now, check whether they are RMA schedulable. Please try out. So, use the completion time theorem to check whether these 3 tasks will be schedulable. You can first try the Liu Layland, right, check if it is schedulable, then you do not have to use completion time theorem. Otherwise, you have to check for every task using the completion time theorem, check if they are schedulable. So, Liu Layland, you will have to find the utilization and then check if it is n into 2 to the power 1 by n less than, I mean the utilization is less than n into 2 to the power 1 by n minus 1, and for 3 tasks it is 3 into 2 to the power 1 by 3 minus 1, which is 0.778. 778. Okay. So, some of you found out that it is schedulable. Let us check the answer. Yeah, so it is schedulable, because if we check the utilization for the 3 tasks, 20 by 100, 30 by 150 and 60 by 200 is 0.7, and by Liu-Layland criterion itself we can say that the task set is schedulable. We need to look no further. Now, let us try a different task set. Let us say 20 100, 30 150 and 90 200 for the 3 tasks. Check whether Liu-Layland criterion is satisfied. Find the 3 task utilizations and sum them up. Not satisfied, right? Is everybody getting? Liu-Layland criterion is not satisfied, but please try the completion time theorem. For every task, please check whether the first deadline will be met. Meeting, right? Yeah, let us see that. So, if we check for Liu-Layland test, the utilization is working out to be 0.85, which is greater than 0.78, and it fails the Liu-Layland test. But before concluding about the schedulability, we will have to check the third criterion, that is the Lehoczky criterion. So, these are the 3 tasks 20 100, 30 150 and 90 200. First, let us try the first task T1. So, let us try drawing the schedule and see what happens, and then we will use the formula. See, the first task is the highest priority because it has the shortest period, and whenever T1 is there, none of the other tasks will be able to run, and under 0 phasing T1 will run and complete by 20, right. So, for T1 the Liu-Lehoczky criterion is satisfied. What about T2? So, T2 is the second highest priority. It will start to run as soon as T1 completes, right. See here, T1 has completed at 20 and T2 will start running for 30 millisecond. So, T2, the first instance of T2 will also complete before the deadline. So, even for this the Liu-Lehoczky criterion is satisfied. 30, sorry, what is 60? Oh, the problem that we had given was 60, is it? 20, 100, not 150, is it? Okay, okay. So, we need to just if it is 60 that was given, so we have to check whether this deadline is satisfied. Let me just verify what you are saying. No, 30, that is okay, no. See, 20 and 100, 30 and 150, 90 and 200, that is all right. So, the utilization is 0.85, fails the Liu-Layland test. Now, the 3 tasks are T1 20 and 100, T2 is 30 and 150, T3 is 90 and 200. So, the first task will complete by 20, meet its first deadline, that is at 100. The second task starts running from 20 and its runtime is 30. So, completes by 50 and its deadline is 150, meets it well before that, is not it. Now, the third task will run for 50 here, 50 millisecond, and by 100 the second instance of T1 will arise, and then T1 will run, and also the second instance of T2 will arise. So, that will also run, and after that only T3 will again run, and it will complete by 190. So, that is within 200 millisecond. So, all the 3 tasks meet their first deadline, and the task set is schedulable by drawing up the schedule. We can also use the formula that we had given. The first task, no higher priority tasks exist. So, 20 is less than 100, satisfied, the Lehoczky criterion satisfied for T1. For T2, there is only one higher priority task, that is T1, each time takes 20 millisecond, and in 150 millisecond it will arise 150 by 100 ceiling, which is 2 times. So, 2 into 20 plus 30 is 70, is less than 150, satisfied for T2 also. And for T3 there are 2 higher priority tasks. T1 will arise 2 times, T2 will also arise 2 times by the ceiling, right. 200 by 100 ceiling is 2, and 200 by 150 ceiling is also 2. So, 90 plus 20 into 2 plus 30 into 2 is 190, is less than 200. So, for this also satisfied. So, the task set is schedulable. Can you quickly try this problem? Whether 3 tasks whose execution time is 10 and the period and deadline are both 50 millisecond and the phase is 100 millisecond, and task T2 execution time 20 millisecond and the period is equal to deadline is 60 millisecond and the phase is 0, and T3 is runtime 30 millisecond, period and deadline is 80 millisecond and phase is 50 millisecond. Will it run satisfactorily under RMA scheduling? So, please work out. Because unless we work out the problem, we will not really understand the intricacy. We will go proceed further from here and check the shortcoming of the completion time theorem. Anybody has no? The answer is negative. Okay. Anyone else? Okay. Let us look at the solution. Please meanwhile try. So, okay, I have not got the solution here, but it is not too hard to try, because we have to consider 0 phasing. If it runs under 0 phasing, then the set of tasks will be schedulable for all phasings. So, the first one will meet its deadline. This has the highest priority. It will complete by 10, whereas the deadline is 50. What about the second one? Second one, it needs 20 millisecond run time, and by this time 2 times E1 will arise, is not it? 60 by 50 ceiling is 2. So, 2 into 10 plus 20, sorry 2 into 10 plus 20 is 40. So, 40 is less than 60. So, even T2 meets its deadline. Now, what about T3? So, T3 runtime is 30 and period is 80, and in 80 2 instances of T1 and 2 instances of T2 will occur, right. So, 2 into 10 is 20, 2 into 20 is 40. So, 40 plus 20 is 60, 60 plus 30 is 90, which is more than 80. So, for the third one, the Liu-Lehoczky criterion is not satisfied, and according to Liu-Lehoczky this is not schedulable. But what do we do if the task set fails Liu-Lehoczky's criterion? Yes, please.
So, earlier in the last example.
Yes.
So,
Last to last, let me just get there. Last to last example. Yes. This is the one, right?
yes, sir.
Yeah.
So, when we drew the schedule.
Yes.
We get the second task completing at 50.
Yes. This one, right?
Yes.
Yeah. Second task.
But when we put in the formula, we get a value 70.
Let us see.
We get a value 70.
Okay, I think the drawing must be incorrect then.
So, the drawing is correct.
Correct,
But
okay.
what we are considering is that we are trying to What we are trying is that we are trying to know how many times the task will
Yes.
appear in the whole period.
Exactly. How many times T1 will occur?
In the whole period.
150. Yes.
Not in during the
Okay.
execution time.
Before the execution. Yes. Exactly. So this formula, say, as he pointed out. Sorry, what's your name? Ashish. As Ashish pointed out, just see here in the formula what we are implicitly assuming that this 20, the task set 2, by the time it will occur, the second instance, sorry, the T2 would not have completed. That is what is implicitly we are assuming, and that is the worst case actually. So, by hand drawing we are getting a more accurate picture compared to this. This is approximation. What he says is correct actually, because here even though the second task occurs only at 100 millisecond, by this time it has already completed T2, but we are taking T1's execution time also into account. So, what will be its impact? Is it possible that by using the hand schedule we can conclude that something is schedulable, and by using this we can conclude that something is not schedulable? Is it possible? Yes, you think so? It will be, we will conclude by using the formula, the expression.
Accommodating for the phase things.
No, phase we have ignored, phase is not there. But let me just please answer this question, that even though you said that the schedules or the completion times for a task is different as concluded by the formula as compared to the hand drawing of the schedule, is it likely that we will get a different result by hand drawing compared to applying the formula? Is it possible?
Even if it does not satisfy the formula, it may be schedulable.
Is it? So, you think so. What about others? It will be schedulable. Okay. In that case, I will just ask you to just construct one example where it fails the formula, but by hand drawing it is schedulable.
The formula depicts the worst case scenario.
Worst case, but see, to convince yourself, just give me one example where by formula it says not schedulable and by hand drawing it is schedulable. Just construct one for me. I think you will be disappointed, not right now, you try later, you will be disappointed, because see here, this we are considering the entire period here, and as long as it occurs within that period, right, within 150, we should consider it in the, that is in the worst case this 20 will be considered anyway. So, you will not be able to construct an example where it will fail this formula and will pass the schedule, I mean hand drawn schedule. Please try that, and if you can construct an example, please give it to me.
So, if the period was 40 and 60 instead of 100 and 150.
So, please try that, convince yourself, and we'll check that. So, let us proceed. Next class or whenever you find, you please construct an example and give it to me. Okay. Let us proceed further. I mean, his observation was nevertheless important, because it is by completion time theorem we are not really saying that task response time 70 is not the task response time, we are saying that whether it will complete by 150 or whatever. If it is response time, yes, there is a problem here, we are not computing the response time, we are checking whether it will meet its first deadline.
So,
and
the periods of 40 and 60, then
so you please try that, you draw the schedule and give it to me, we will display that. Okay. So, now what if a set of tasks fails Liu-Lehoczky criterion? Can we conclusively say that the task set is unschedulable, or is there a necessity for further check? Actually, Liu-Lehoczky checks the worst case scenario, that is the 0 phasing case, but if the phases are non-zero, then it is possible that the Liu-Lehoczky's result is negative, but we have the task set schedulable because of the phase between the tasks. Now, a very basic question, let us try to understand. See, for most of the task set, you try to draw the schedule using EDF and RMA, you will find that they have the same schedule. You just try out, take any set of tasks, let us say T1 is 20 and 50, T2 is 30 and 100. Check the EDF schedule and RMA schedule. Is it different or is it the same schedule both RMA and EDF are giving? So, check 20 and 50 and 30 and 100 are 2 tasks. So, let me just write here. So, T1 execution time is 20 and the period deadline is 50, and T2 execution time is 30 and period and deadline are 100. So, the schedule according to EDF is, it will start with T1 that has the earliest deadline. So, let me draw for EDF. It will start with T1 because that has the earliest deadline, and it will run up to 20, and at 20 T1 has completed and T2 will run for 30, and again T1 will run and again T2 will run and so on. Now, if you try out RMA, same thing, T1 runs, it has the higher priority, and after that T2 runs, after that T1 runs, T2 runs. So, both EDF and RMA are producing identical schedules for this task set. You will find that for many task set, they are scheduling identical schedules. Can you construct one task set for which they produce different schedule? That will help us to understand the behavior of.
For example, for T2, we have, there will be a gap, I think, 100, after 100 T2 will appear.
T2, okay. See, for both of them, let us draw again neatly. Yeah, what he says is correct. So, T1 runs for 20, then T2 runs for 50, sorry 30, and by that time T1 does not, okay, T1 exists by that time, is not it? So, T1 has arisen by that time, runs up to 70, and by that time T2 does not exist, it arises only at 100, and by 100 again T1 exists, right. So, T1 will run and then at 120 T2 will run, is not it, for 120, 150. So, this is the EDF. Now, let us try the RMA. So, T1 runs up to 20, then T2 runs up to 50, and by that time T1 again arises, runs up to 70 and after 70 there are no task instances to run, and again at 100 we have T1 arising and that has higher priority. So, T1 will run up to 120 and after that T2 will run. So, identical schedule both EDF and RMA. Can you just construct one example where EDF and RMA produce different schedules? That will give us some understanding into the scheduling policies of EDF and RMA and how they are different. So, just construct one example of a task scenario where T1 and T2, sorry, where RMA and EDF we will have different schedules. Please think about the basic principle between EDF RMA, their schedulability, that is the scheduling constraint, and that should give you some hint. Anyone thinks of some example? Okay, not too difficult. Let us see the answer. See, the simplest answer is that when something is unschedulable by RMA, but is schedulable by EDF, definitely their schedule will be different, is not it? Because by this schedule RMA is not able to schedule it. So, EDF must be using a different schedule, is not it? That is one hint. I mean, this is the simplest answer to construct a task set which is have different schedule under RMA and EDF. Another example.
But sir, we have said that RMA is an optimal static uniprocessor.
But EDF is a dynamic.
Yeah, exactly. See, something not schedulable by RMA will can be schedulable by EDF, because EDF is a dynamic priority algorithm. But if anything is not schedulable under EDF, RMA cannot schedule that. So, this is one example, simple example where they produce different schedules. But suppose we say that, see, give us an example where the task set is schedulable under both RMA and EDF, but the schedules are different. In that case, we have to consider the task set in which the task is preempted before completion. So, possibly the example that we are just seeing, the 3 tasks where the task T3 was getting preempted, right, before it could complete, another task is to arise and preempt it, and that is the situation where these two will produce different schedule. Please think about it, why they will produce. Sorry, EDF is also preemptable, but what I am saying is that in RMA scheduling, if the one task is getting preempted, in EDF it may not be preempted, because it will already having the deadline very near. So, just because it had a higher priority does not, static priority does not mean that it will preempt it in EDF. In EDF it will check the deadline each time. So, the preemption condition for both these algorithms is different. So, if you consider the preemption case, task preemption case, you will find that they construct different schedules. Okay, let us proceed further. So, please try out some examples for your understanding. Okay, this is one example where they produce different schedule. See, task E1 sorry, task T1, the execution time is 3 millisecond and period is 8 millisecond, T2 is 6 and 12. So, T1 has higher priority, runs up to 3, and then T2 runs up to, it should be 9, is not it? Yeah, it should be 9. So, it runs up to 9 and then 8, is it? Okay, okay, T2, okay, sorry. No, it runs for 3 and then, acha, right, it runs up to 8 and gets preempted here. That is what we are saying, it is getting preempted here because of the static priority. Just check here that at this point T2's deadline is at 12. Right, T2's deadline is at 12 and T1's deadline is at 16, right. So, T1 has a further deadline than T1 and T1 should not preempt T2 according to EDF. So, if we check the EDF, that is what happens here. So, T2 will complete and then only T1 will run, right. On the other hand, here just because T1 had a higher priority, it is preempting as soon as it has arisen at 8 and it will take this 3 to complete. Different schedules of RMA and EDF. Looks okay? Okay, let us proceed. We had said that EDF behaved very poorly under transient overload, but let us see the RMA behavior under transient overload. We will see that RMA is stable under transient overload. When does transient overload occur? Can anybody answer this question? Why does a transient overload occur?
When we have many events.
Okay. So, one situation is that one event is giving rise to many tasks suddenly, system will get overloaded. Like we were saying that a fire alarm, a fire situation was sensed and many tasks had to be started. There can be other situations also, like one task for some reason starts getting late. So, the system will get overloaded. So, let us see under both these situations. One is a task is getting late due to whatever reason, possibly that it took a branch which was not usual and it started taking more time in that branch or got into an infinite loop, and many reasons actually. So, when a task gets late, according to EDF, its priority will keep on increasing because its deadline is approaching, is not it? But here the priority is static, whether it gets late or not, it will be preempted as soon as there is a higher priority task. So, it cannot block a higher priority task just because it is getting late. As long as there is a higher priority task, unlike EDF, the CPU must be yielded by a lower priority task. And the other situation also, where we have many tasks arising suddenly, there also the highest priority task will never miss its deadline, because that is the basic of this scheduling algorithm. So, it is stable under transient overload. Now, let us see what are the possible implementations of RMA, because most of the commercial operating system, many of them will see that they just give you facilities to set priority statically and then you implement the RMA. The most simplest implementation is a first in first out queue. Insertion is simple, is efficient. O1, whereas searching you have to search all the tasks, so that is ON. So, considering the number of searches you have, it is very inefficient. A better implementation would be to maintain a priority queue, and here insertion is log n and searching is O1. But a more efficient implementation is a multi-level feedback queue. So, in a multi-level feedback queue, what we have is we arrange the tasks in different queues, their priority order. So, 1 is the highest priority, 6 is the lowest priority. Now, when you insert a task, you just insert in the appropriate queue based on its priority, and when you select the task, you start looking from the highest priority. If something is available here, some task, run it, if not, look at the next one. So, what is the insertion time and the searching time? Yes? Consider the average case. So, that is a assignment for you. Please compare the efficiency for the simple implementation, the priority queue and the multi-level feedback queue. Just do some analysis and so which one will be better by how much. You can make any assumptions that you feel like. like how many tasks, you can consider a bound on the number of tasks and the bound on the number of priority levels and so on. So, please submit your answer on the analysis of the implementation. If there is a good answer, we will give some bonus marks for the answer. So, that is analyze the time and space complexity for the multi-level feedback queue and compare with the other implementations. There is no time limit on when you want to submit the answer, but once somebody submits answer, we will not consider the other answers unless there is a significant difference in the thinking procedure, etc. So, now let us check the case for harmonically related tasks. We call a set of tasks harmonically related if whenever we take a pair of tasks Ti and Tk, if the period I is greater than Pk, then Pi will be n times Pk, where n is an integer. For example, for 3 tasks whose period is 10, 20 and 60 are harmonically related, because 20 is 10 into 2, 60 is 3 into 20 and 6 into 10. So, every higher period is an integral multiple of every other lower period. Then we call it as a harmonically related set of tasks. The interesting result is that if a set of tasks the periods are harmonically related, then they are RMA schedulable if their utilization is less than 1. So, as long as so the Liu Layland criterion was giving 0.778 and so on, but here you see that for harmonical tasks you are able to get almost 100% utilization. Please think what is the reason. Okay, we will show it more formally in the next hour, that why it is less than 100% is a sufficient condition for a harmonic set of tasks. So, we will stop here, we will continue in the next class.